All right, we're going to start here. Okay, we're ready? So, just a real quick recap of first order circuits because Ursula asked about that. Again, the only first order circuits that exist in the world will look either like this or like this. Because all you have to do to get it to look like this is if your circuit has an inductor, you find the Norton equivalent of the rest of the circuit. And there you have it. If it's a capacitor, you find the Thevenin equivalent. And there you have it. So in these circuits, we define the current through the inductor, or in this case, the voltage across the capacitor. And then whatever voltage source is acting here, then, it's going to be some function of time. It might be constant, it might be zero, it might be sinusoidal, it could be anything. Each of these circuits has a differential equation that describes it, and it's a first order differential equation. And if you do the math, this is it. This is the differential equation. Now, you say, well, wait a second, what's x, and what's tau, and what's y? I mean, we've got I and V and R and L, so what are these things? Well, depends on the circuit. Here's the key. If you've got the RL circuit, x is the current through the inductor. If you've got the RC circuit, x is the voltage across the capacitor. Tau for the inductor current circuit is L over R. If you've got the capacitor circuit, it's R times C. That forcing function here, the function of T that's on this side of the differential equation, if it's the inductor circuit, it's merely whatever this current source is, divided by tau. So it's not exactly, this y of t isn't really the current source, but it's certainly related to the current source. It's the current source divided by tau. The voltage, and then similarly, y of t, if you've got the capacitor circuit, it's this. So this is the key, or the legend, I don't know what you want to call it, but this is what this equation becomes for the specific circuits, whether you have the inductor or the capacitor. So remember, it's just like any circuit that has energy storage elements. You find the differential equation, then you solve it. So all first order circuits have this differential equation. The solution to this differential equation is this right here. This is in case you're interested, this is the natural part, this is the forced part. So there's the solution. You can use that for any first order circuit. So you don't even really have to think about all this. Just boom, go to the solution and make sure that you just know what tau and y of t are. That's all you need to know. You might ask, well, what's k? K is that arbitrary constant that is determined from the initial conditions. So once you substitute in tau and y of t, you do have to find k just by applying whatever initial condition you have for that circuit. And then one step further, okay, so this is the most general form of the solution. If you know that these sources are constant, so you have a DC circuit, then you can even skip this kind of ugly equation and just go directly to this equation. And this is my favorite form of it. The book had a couple of other forms, but this one is the most useful because here, all you have to do is by inspection, find out what the long-term, current or voltage is. Because remember, x is either the current through the inductor or the voltage across the capacitor. You can easily do that just by looking at the circuit. Because remember, inductors act like short circuits in a DC current, DC circuit, and capacitors act as open circuits. So this is a very easy term to get. This needs to be given. You need to know what the initial voltage or current is, and that usually is either it's given or you might have a switch in the problem and you know what's going on right before the switch closes, and so that means that the voltage across the capacitor is going to be the same right before and after the switch closes because we know those voltages across capacitors cannot change instantaneously. So for some, somehow you got to get information about this initial condition. And there you have it. So that's kind of the recap of the first order circuits. This equation, it might look a little bit ugly, but it really is nothing that you can't handle because you know how to integrate. At least I'm assuming that you've taken your calculus courses and you know how to integrate. You just, whatever the function is, y of t, which in, the case of the inductor circuit, it's just going to be your current source divided by that constant tau. You just stick it in and then you integrate. So, the math might get a little tricky, but I'm assuming you know how to integrate and you can just kind of plug in these things and figure out the answer. Okay, so I had a request to do a source transformation that was, not just a straightforward source transformation. So I'm hoping this fits the bill. So we're asked to find R of L if I is 2 amps. So we need to simplify this. I mean, there's a lot of different ways we can do it, but I'm going to do it by source transformation. Okay, so the first source transformation is a more straightforward one. So I'm going to transform this 24 volt voltage source in series with the 4 ohm resistor into its equivalent Norton circuit. So, okay, so looking at it from A and B. So, you're looking at it from A and B. Need more room. And so the resistor is still going to be 4 ohms, right? But the voltage source is going to become a current source, and the relationship between the current of that current source and this voltage source is basically Ohm's law, so that, don't laugh at me, V equals IR, so I equals V over R. So it's going to be 24 divided by 4, so it's going to be 6 amps. Okay, so that was the more straightforward transformation. Okay, now I want to transform this into, okay, again, I've sort of got a Norton, a 7-in, but I want to transform it into a Norton so that I have all these things in parallel and then I can reduce it. Okay, this is a little bit harder. So I'm going to do a little bit of, because it's, it's not just like, ooh, you're kind of looking at that and it's like, how do you do it? So I'm going to do it by kind of stretching my wires and looking at it. Okay, now this might be a little contrived, but bear with me because I think it'll help you visualize it. Okay, so I could actually do this, right? And it's not going to change the problem. And I'm going to kind of do that, just kind of pull it out here. And that's not going to change the problem, is it? I haven't changed the problem. But now I'm going to kind of look at this. I'll label this C and D from the perspective of C and D. And so here's C. Here's D, and now I'm going to do that source transformation. So again, I've got 12 ohm resistor in series with a 12 volt voltage source, and so I've got the 12, so I can do it like this. So this is 12 ohms there, and then I've got the current source. Okay, be a little bit careful because the negative sign is on top, so that means that the current is going to be going down like that, and the value of that is going to be 12 divided by 12, right? I erased it, but I equals V over R, so 12 volts over 12 ohms, this is going to be 1 amp. Okay, and then, okay, watch carefully because I'm about to kind of do this little bit of erasing. I think you'll agree with me that what I have here, we can easily just go ahead and you know, make it so that all of these come into this node C, kind of that idea of stretching it, stretching these wires so that they just kind of look a little bit different, but I haven't changed the relationships. Okay, and now I think you can see we just got these in parallel. They're all in parallel. And then, what happened to the, oh, okay, and then I've still got that 5 volt. Okay, so I still got this 5 volt and then RL here and 2 amps here. Okay, so now what I can do is I've got 1 amp parallel with 1 amp. So I can redraw that as, okay, 1 amp going down, 6 amps going up is equivalent to 5 amps going up, like that, right? And then I've got 4 ohms in parallel with 12 ohms. Oh, help me out here. 4 times 12 divided by 4 plus 12. What is that, 48? That's 3. Thank you. Okay, so now all of this has been transformed into 5 amps and 3 ohms. And then I've got this, 5 volts. Okay, so I want to do another transformation. Okay, I think the rest of this will be straightforward because now you're just looking at it here. You can transform this back to a voltage source in series with resistor. I'll just do it real quick. So that would make this 3 ohms here, and then this would become a voltage source, V equals IR, so it would be 15 volts. And now 15 volts minus 5, right, because the polarities are different, will make this 10. I know I'm doing this really quick, but you can replay it. Now I've got 10 volts and 3 ohms. Okay, so now we can finally see really quickly here that I has to be 10 divided by 3 plus RL. So if I is 2, go ahead and solve for RL. It should be 2 ohms, the final answer. Okay, cut.